This lecture is about conductors, resistors, and Ohm's law. What defines a conductor is that electrons can freely move around inside it. That means also that any electron holes, essentially any deficit by one electron, can freely move as well. So that inside a conductor, negative and positive charges are freely moving around. So for example, here's a conducting block of metal. It's immersed in a uniform electric field. In response to this, electrons, negative charges, will move to the left side of the block. Meanwhile, the holes that they create, those absences of electrons, will all move to the right side of the block as far as they can in response to the electric field, because these are behaving essentially as positive charges, so they're going to move in the direction of the electric field pointing. And this movement will continue until these positive charges that have migrated to the right and negative charges that have migrated to the left have moved to create an electric field inside the conductor that exactly cancels the external electric field that already exists. As a result, there's no electric field inside the conductor. So anytime you have an electric field, electrons will move against it, and the positive charges or electron holes will move with it until enough have moved to exactly cancel that electric field. Once the electric field inside the conductor is totally canceled out to zero, then no more will move. So as a consequence of this, inside a conductor, the electric field is always zero. Now this tells us something about the voltage, because the change in voltage anywhere between any two positions is the electric field between those two positions times the displacement between those two positions with a minus sign. Since the electric field does not change, since the electric field is zero, that means the voltage does not change, so the voltage is uniform throughout a conductor. Another way of saying this is that the entire conductor is at equipotential. Now this means that the surface of the conductor is an equipotential line. And since the electric field is always perpendicular to equipotential lines, this means the electric field is always perpendicular to the surface of a conductor. Let's explore some consequences of these facts about conductors. Suppose we have a thin conducting shell, and we immerse it in a uniform electric field. Well, it doesn't actually have to be uniform, it could be any electric field. The fact that the conductor, the thin conducting shell, is all at equipotential means that there's going to be no electric field inside the conductor. This is called a Faraday cage. It's named after the physicist Michael Faraday. So if a conducting enclosure like this can block electric fields, the question is, what can we do with this? Well, if you look online, you can find a story of an electrician. The company that he worked for required him to carry with him a GPS-enabled phone so that they could always track where he was and make sure he was working. Now, GPS works by communicating with GPS satellites via electromagnetic signals. Now, this electrician also liked to eat bags of chips. And he realized that the bag of chips, they're lined with a bit of foil, and this means that once he's eaten all the chips, the bag of chips can function as a Faraday cage. He then got a brilliant idea. He could put his phone in the empty chip bag, and the Faraday cage would block the GPS signals. This meant that his company couldn't track his location, and so instead of going to work, he could just go play golf. Seems like a good idea, but then he got found out and got fired. I found another story of a pub owner who noticed that a lot of his patrons were spending time on their phones instead of talking to each other. So he installed copper wires and foil through the windows, through the walls and the ceilings of his bar. This blocked the electromagnetic cell phone signals from coming inside the bar, and so phones no longer worked. And then he said everybody talked to each other in the bar instead. Now we can use conductors, of course, to make circuits. We can connect conducting wires to two ends of a battery. And then on the other end of these wires we can connect them by a resistor, which looks something like this, and the colored bands on the resistor indicate the strength of the resistance. So when we do a lab on resistors, you'll see resistors looking just like this. Now in electronic symbology, a battery is indicated by this symbol. The longer line indicates the positive side of the battery, and a resistor is a zigzag. Now if the voltage difference in a battery is 1.5 volts, and let's say this side of the battery is at 0 volts, then this side is going to be at 1.5 volts. And because this is a conductor, it's all at equipotential, so that means there's also going to be a voltage difference across the resistor of 1.5 volts. We call that voltage difference V, and Ohm's law simply says that the voltage difference across a resistor is equal to the current flow through that resistor times its resistance. Now the current I is defined as the number of coulombs of charge flowing through the wire each second. So it's got units of coulombs per second. Given that voltage we already know is a number of joules per coulomb, we can determine that the units of resistance must be joule seconds per coulomb squared, and that's kind of a mouthful, so we write simply the Greek letter capital Omega and we call it ohms. Now remember that power is joules per second. With these definitions of current and voltage, we can write simply that power is equal to the coulombs per second times the joules per coulomb, so that the coulombs cancel, and power is then the joules per second. And we recall from when we defined power before that this is called, a joule per second is called a watt. So the coulombs per second is I, and the joules per coulomb is V, so the power going through a resistor is equal to the current going through it times the voltage. And using Ohm's law, we can rewrite that either as I squared R or V squared over R. So let's do a sample problem. Suppose we're going to hook up a 1.5 volt battery, just a AA battery, to a light bulb with a resistance of 1 ohm. First we'll ask, what is the wattage of this light bulb connected to this battery? Well, the power is equal to I times V, which is equal to V squared over R, or 1.5 squared over 1, and this comes out to 2.25 watts. Now let's ask, how long does the battery last? Well, a typical AA battery has a capacity of about 2500 milliamp hours. Now typically capacity is reported this way, but a milliamp is just 1/1000th of an amp, so we can just call it 2.5 amp hours. And what does this mean? Well, it means essentially that the battery can provide 2.5 amps of current for a single hour, or 1 amp of current for 2.5 hours. More generally, it means that 2.5 amp hours is just the current times the total time for which the battery provides that current. So that means we need to determine the current. It's I equals V over R from Ohm's law. V equals IR rearranged to solve for I, and that's 1.5 amps. And so T, which is equal to 2.5 amp hours divided by 1.5 amps, or about 1.7 hours. Now I should note that these battery capacities reported this way are a little bit of a simplification. The effective battery capacity depends on how quickly you drain it. So this kind of, taking these battery capacities at face value is only an approximate result. So for homework, do a similar problem. This time we'll have it running on a 9-volt battery, a flashlight with a 1-watt bulb, and the battery has about a 300 milliamp hour capacity. How long will this flashlight last?